In nature, we can differentiate between materials based on the property that they have free electrons or not. First, we have insulators. They have no free electrons. That is, in insulators, each electron is attached to its parent atom and it is not free to move about. Therefore, insulators have no free electrons, and the opposite of insulators are called conductors. Conductors have free electrons. That is, in conductors, there are few electrons that are free to move about, and those electrons are not attached to any parent atom. They can move freely through the material. For example, metals are conductors. In metals, there are many free electrons, and those free electrons are free to move about. Therefore, metals act as good conductors of electricity. Now, let us study a few properties of these conductors. First one is that the electric field inside the conductor is equal to 0. Let us imagine that we have some external electric field in this direction, that is going from left to right. This will be the external electric field. I'll write X for external. Now, let's say that we keep a conductor in this external electric field. Then due to this external electric field, the positive charges of the electron will experience a force towards the right, and the negative charges will experience a force towards the left. Since force is equal to charge times the electric field, if the charge is positive, the force will be along the electric field. Therefore, for positive charges, they experience a force towards the electric field, and for negative charges, there will be a minus sign. Therefore, negative charges will go against the electric field. So, the overall effect of the external electric field is to induce positive charges on the right side, that is on the right surface of the conductor, and induce negative charges on the left side of the conductor. Now these charges will produce an electric field of their own, which will go from positive to the negative charges, like this. Let us call it EI for induce. Now as we can see, the induced electric field will be in the opposite direction to that of the original external electric field. The induced electric field will cancel the effect of the external electric field. So it will be negative but equal to the external electric field. And this whole process will be instantaneous. Therefore, the net electric field inside a conductor will always be equal to 0. This is one of the most important properties of the conductors, that is, the net electric field inside the conductor is always equal to 0. Next, the net charge density inside the conductor is equal to 0. We can explain this in this way. Since we know that the divergence of electric fields is equal to rho by epsilon naught from Gauss's law, and rho here will be equal to net charge density. Now we know that inside a conductor, let's say this is a conductor, the electric field is 0 at all points. Now, if the electric field is 0 at all points, therefore when we differentiate 0, which is constant, the differentiation will also be equal to 0. Therefore, the divergence of electric field will be equal to 0. Therefore, from this, we can say that rho will also be equal to 0. That is, the net charge inside a conductor is always equal to 0. Net charge density inside a conductor is always equal to 0. To be clear, there might be positive and negative charge densities, that is, there might be positive and negative charges, but the net charge density will always be equal to 0 inside a conductor. since the electric field inside the conductor is equal to 0. Third property is that any net charge, that is, any charge that we provide or any leftover charge on the conductor, will reside on the surface of the conductor. Since in the previous case, as we saw, that the net charge density inside the conductor must be equal to 0, since the electric field was equal to 0, therefore the only place left for the charges that we put on the conductor or any net charge will be to flow over to the surface of the conductor. So the charges will reside on the surface of the conductor, not inside the conductor but on the surface of the conductor. Therefore, let's say we have some conductor and we provided some charge Q, then this charge will distribute over the outer surface of the conductor. And the distribution of this charge Q will be in such a way that the electric field at any point inside the conductor will be equal to 0. Now, let's talk about the properties of conductor when we have a cavity inside the conductor. A cavity is a hole inside the conductor like this, where there is no meat of the conductor, where there is no more conductor. Therefore, this will be a cavity inside the conductor. And let's say that we provide a charge Q to the conductor. This charge will distribute itself on the surface of the conductor, on the outer surface of the conductor, in such a way that the electric field inside the conductor will be equal to 0. But if the cavity does not have any charge, then the electric field inside the cavity, I will write C, must also be equal to 0. We can explain it in this way. Let's say that this is our conductor, and then we have a cavity over here. Now, let's take a point A and point B and connect them via some path that passes through the conductor, like this. Now, since we know that inside the conductor, electric field is equal to 0 at every point, therefore the line integral from A to B, E dot dl, will also be equal to 0 along this path. Now, let us take some other path which passes through the cavity, like this. Now, as we know that the line integral is independent of the path, if we go along the path that passes through the conductor and we find that the line integral is equal to 0, then the line integral through the cavity must also be equal to 0. Therefore, the line integral through cavity, so I'll just write cavity, just so we know that it passes through the cavity, E dot dl must also be equal to 0. And now, dl will always be along the path, so this will be the direction of dl. And let's say that there was some electric field. Let's suppose that there is some electric field inside the cavity, and we take a path along the electric field. So the electric field will also be along the direction of dl. Then there is no way for this E dot dl to be equal to 0. Since when we integrate E dot dl, we will always get some positive value for this line integral as we go from point A to point B through this path, that is through the cavity. So in order for this line integral to be equal to 0, there must be no electric field inside the cavity. Therefore, we can say that electric field inside the cavity is equal to 0 inside the cavity must be equal to 0 when there is no charge on the inside the cavity. This is very important. There must be no charge inside the cavity. Then and only then will the electric field inside the cavity will be equal to 0. To be clear, there might be some other external charges, let's say Q external, that might lie around. The net effect that this external charge and the charge Q that we provide will be that the electric field inside the conductor and inside the cavity will be equal to 0. Now let's say that we have a conductor and we have a cavity, and now if we put in a charge Q, then this, let's say it is a positive charge, then this positive charge will attract negative charges towards it. That is, it will induce negative charges on the surface of the cavity, that is on the inner surface of the conductor, that is this one. On this surface, negative charges will be induced, and the negative charge induced will be equal to the positive charges. Why? Let's enclose this cavity in a Gaussian surface. Now, since this Gaussian surface is inside the conductor, where the electric field at all points is equal to 0, electric field at all points inside the conductor is equal to 0, therefore this whole integral will be equal to 0, since the flux will be equal to 0. And from Gauss's law, we know that this term will be equal to the charge enclosed divided by epsilon naught. Since this integral was equal to 0, the charge enclosed must also be equal to 0. Now we have provided the charge Q, positive. Therefore, in order for the net charge to be equal to 0, the induced charge on the wall must be negative Q. Since then and only then the net charge enclosed will be equal to 0. Therefore, when we put a charge Q inside the cavity, it will induce an equal and opposite charge on the walls or on the surface of the cavity. Now, since the conductor as a whole was electrically neutral, the negative charges must have come from the conductor. Therefore, the conductor is now left with equal and opposite positive charges over its surface. And if we had already provided the conductor with some charge Q, let's say, then again the process would have been the same. Only now the positive charges would have increased. So there would have been more positive charges. Now, let's talk about the electric field in this case. That is, we have some conductor, we have some cavity, and we put a charge Q. This will induce negative charges on the surface of the cavity. Since the charge Q is positive and it has induced negative charges, there will be some electric field inside the cavity in this case. Unlike in the previous case where there was no charge in the cavity, the electric field was equal to 0 then. But now we have a charge Q. And this charge Q has induced opposite charges on the walls of the cavity. So there will be an electric field. Inside the cavity. It will not be equal to 0 in this case. Electric field due to this charge Q and the induced negative charges will be such that the electric field at all points inside the conductor and also outside the conductor will be equal to 0. Therefore, when we have a charge Q, it will induce an equal and opposite charges on the surface of the cavity. And the net effect of those induced charges and the charge Q is that the electric field at all points inside the conductor and also outside will be equal to 0. Now, the electric field in this case will be the electric field due to the charge Q plus the electric field due to the induced charges. I'll just write I. And also, if we had some other charges lying around, let's say again we take cavity Q and it will induce some charges on surface and which will in turn be left with opposite charges over here. And let's say we have some external charges. Again, the net effect of all the charges, that is the external charge, the charge Q, induced charges on the cavity and on the outer surface of the conductor, is that the electric field will always be equal to 0 inside the conductor. The electric field due to the charge Q and the induced charges on the walls of the cavity will separately be equal to 0 inside the conductor, and the net electric field due to all the charges will again be equal to 0 inside the conductor. And the electric field due to the charge Q and the induced charges on the walls of the cavity will be equal to 0 at any point outside the conductor. But it is not necessary that the electric field due to the external charges must also be equal to 0 at any point outside the conductor. Only the electric field due to the charge kept in the cavity and the induced charges on the walls of the cavity, the net effect of those electric fields will be that the electric field will be equal to 0. And this electric field will be due to the electric field of Q and the electric field of induced charges. So these were the properties of the conductors.